So this is another free response question. This time it's from 2008 on the AB exam, problem number 2. This is definitely a calculator problem. And the situation is that concert tickets are going on sale at noon, and that corresponds to the time of 0, and we're sold out within 9 hours. So what we have access to in this table is we have values of L of t, and L of t is going to measure the amount of people waiting in line at each of these times. So we know that at 1 p.m. we had that many people in line, 3 p.m. that many, 4 p.m. that many, and so on, until at t equals 9 they're sold out and they have no more people waiting in line to buy the tickets. They tell us that L of t is twice differentiable and is defined on the interval from 0 to 9, and then we have the selected values of L of t. In part A it says use the data in the table to estimate the rate at which the number of people waiting in line was changing. So this is the key word in that first sentence. If you want to estimate a rate of change, you're looking for a derivative. The rate of change of the number of people waiting in line at 5.5 is going to correspond to this, L prime of 5.5. Now, we don't have the capability of finding this because we don't know what L of t equals. If we knew what L of t equals, we could take the derivative, toss 5.5 into it, and place a t and evaluate. But in this case, we need to estimate this. So we can estimate an instantaneous rate of change, the slope of a tangent line, by using the slope of a secant line. We have these two ordered pairs right here. And 5.5 would kind of sit right smack dab in between these two t values, right? It would be 1.5 above 4 and 1.5 below 7, 5.5 would be. So what we can say is we can say the derivative, or the slope of the tangent line at 5.5, is going to be approximately equal to the slope of the secant line connecting these 2 points on the graph of L of t. So if we just go ahead and go right into a slope calculation, if we take the difference between the y values, so 150 minus 126 over the corresponding difference between the x values, or the t values in this case, so that'd be 7 minus 4. This is a calculator problem. I think we can manage with this particular calculation without a calculator, though. I think in that numerator you're looking at 24 when you take the difference. In the denominator you're looking at 3, and this is going to be 8. It does say to show the computations that lead to your answer. We obviously have done that. It says to indicate units of measure. So the units of measure would be, well, just think about the units in the top and bottom here. In the top we have two things that are measured in people, so the units here would be people per, well, in the bottom, 7 and 4, those are values of t. T is measured in hours, so that'd be people per hour. So at 5.5, we had about 8 more people per hour joining the line at that time. If we check out part B here, part B wants us to use a trapezoidal sum. So a trapezoidal sum is used to approximate an integral, we have to remember. It says to use 3 subintervals to estimate the average number of people waiting in line during the first 4 hours that tickets were on sale. So the average number of people waiting in line. Well, L of t represents the number of people waiting in line. If we want the average number of people waiting in line, I think it makes sense to try to break out this formula for the average value of a function, 1 over b minus a times the integral from a up to b of whatever function it is that we want the average of. So this is the formula for the average value of a function, which we've used off and on for the last couple weeks. We want to apply this formula to the function L of t on the interval from 0 to 4, right? The first 4 hours that tickets were on sale would be the hour 0, noon, to hour 4, 4 p.m. And we're going to have to estimate this with a trapezoidal sum. We don't have the capability of evaluating the integral. We're going to have to estimate it with a trapezoidal sum. So we can go ahead and make this formula fit what we're trying to do here. 1 over 4 minus 0, right? We're applying this formula to the function L of t on the interval 0 to 4. Here we're going to have our integral from 0 up to 4 of the function we're looking for the average value of with respect to t. we're going to have to estimate this with a trapezoidal sum. So that's going to be approximated by, and if you're ever concerned with how to build a trapezoidal sum or a Riemann sum, what you can always do is you can always get yourself a graph, and it doesn't have to be a perfect graph, but it should give you a way to kind of visualize what the dimensions of the figures that you're adding the areas of together actually are. So I'm just going to plot the point 0, 120. We'll go 1, 2, 3, and 4. So that's 0, 120. 1, 156 is going to have to be above that a little bit. 3, 176, so over 3, and then up to 176 is going to leave me about right there. And then down to 126 at the t-value of 4, which should leave me just slightly above where this one was, right? Because that has a y-value of 120. So 4, 126 should sit about right there. So we just have this quick little sketch of a graph where all we've done is plotted these 4 points on it. And what we're going to have to do is we're going to have to find, to carry out this trapezoidal sum properly, we're going to have to find the area of this trapezoid, the area of this trapezoid, and the area of this trapezoid. We're going to have to add those areas together, and we're going to have an estimate for this. The only other thing that we're going to have to do with that number once we develop it is we're going to have to multiply it by 1/4 to turn it into a calculation for the average value of this function. So let's see, this first trapezoid right here. To find its area, we need to take the average of the parallel sides, so we need this height plus this height divided by 2. So that's going to be 120 plus 156 over 2 times the distance between those parallel sides. Well, that would be 1 unit along the t-axis there. We're going to add to that the area of this trapezoid. Now this trapezoid has a width of 2 across the bottom, a distance of 2 between the parallel sides. So in this set of parentheses, we're going to have a 2 multiplying the average calculation for the parallel sides. And the parallel sides would measure 156, would be this one, right? It's the same edge as the right edge of the last trapezoid, so we're going to have 156 plus this height would be corresponding to L of 3, which was 176, divided by 2. And then we need one more trapezoid's area. This last trapezoid is back to a width of 1, so we're going to have 1 as the coefficient over here. And then the average of these parallel sides, well, this was the right edge of the last trapezoid, and it also happens to be the height of the left edge of the last trapezoid. And then this y value right here is going to correspond to L of 4, and L of 4 is 126. So it's a calculator problem, so once you have this expression composed, you can go ahead and you can toss this into your calculator. The only other thing that you're going to have to realize is that this is just estimating the integral here. It doesn't take into account this 1/4. So whatever the answer for that sum is, we're going to have to make sure we multiply it by 1/4 to turn it into an average value of the function calculation. So we estimate the value of the integral with this, we multiply it by 1/4, and we get our result. And so that result should end up being 155.25. So I just took a break from the video there to try and toss that into the calculator, and I got 155.25. Now something that was kind of interesting that happened to me whenever I did this was I first typed this expression in, thought I evaluated it right, and I got an answer that was like 175 point something. And so I knew it was wrong because I kind of said, well, if I'm saying the average number of people waiting in line is 175, that doesn't make a lot of sense, because at 3, whenever we kind of had the most number of people waited in line that we're able to see here, that number was just slightly above that 175 mark. So I knew there was an issue, and I had typed a number into the calculator incorrectly, and so I reevaluated, and I got a number that makes sense. It seems to make sense to say about 155.25 people were waiting in line, because we see a value smaller than that, we see a value, another value smaller than that, a value considerably larger than that, and then a value that's kind of right near that number. So that makes sense, and we'll do parts C and D in the next video.